Hi all. Now we're on chapter 9, which is on duration, convexity and immunization. So these are the scope. First we will be introduced to the purpose of this topic, and then we'll touch on duration, convexity and immunization. Okay, first, what is the purpose of this topic? Basically, it will assist investors that hold many fixed income investments to be able to measure the impact of the change of interest rate on their net position. Net position means their asset minus their liability, because the change of interest rate will impact both their asset and their liability. Also, this topic will assist the companies to protect themselves from the adverse impact of the interest rate change by using some immunization strategy. We will discuss the strategy later. So let's try to understand what is the impact of the interest rate change on fixed income asset. Okay, this one is on single cash flow assets or zero coupon bonds. So we have two zero coupon bonds with different time remaining, which is different duration. This one is 10 years, this one is 20 years, at 6% yield rate. So when the yield rate changed, basically there is an increase of 0.1% yield rate. What happened to the price of the bonds? So higher yield means lower bond prices because it is discounted more. So how much lower? So the new price is 553 and 305. So the percentage of change as a percentage of the original price is negative 0.94% and negative 1.87%. So the percentage change is a lot higher for the 20-year zero coupon bond. This means to show that the price sensitivity of an asset with a higher duration is going to be higher. So they are more price sensitive. So price sensitivity is dependent on the duration. Okay. So let's understand a bit more. So for a zero coupon bond, relationship between the price and the yield is a curve as follows. So this is the price and then this is the yield. So it will be a curve as follows, and then each duration will have its own curve. So the orange is for 10 years duration and the grey is for 20 years duration. So you can see the curve, the slope is a lot steeper for the grey one. So we can say that the price is more price sensitive for the higher duration. So here we can see price change, percentage change in price per change in yield is dependent on the price sensitivity, and this price sensitivity is dependent on the duration. For a single cash flow bond, its duration is simply just the time remaining. But for a duration for a multi cash flow, it is more complex. We will discuss it in the next slide. So now how do we compute the duration for a multiple cash flow asset? So a multiple cash flow asset actually can be split into several single cash flow assets, right? So in this example, it can be split into 5 single cash flow assets. 1, 2, 3, 4, 5, right? So the Macaulay durations that we will calculate to represent the duration for these multiple cash flow assets is the weighted average of the durations of all of the single cash flows involved in this multiple cash flow asset, and the weight. So we want to calculate weighted average. What is the weights used? The weights is going to be based on the present value. So for example, what is the weights for the first cash flow, it will be the present value of the first cash flow over the total present value of the cash flows, which is the price of the asset. So the price is 956.7. So this will lead to 4%. So that is the first weight. The remaining weights is computed with the same method. So you get the following weights. So now we can compute our Macaulay duration, which is the weighted average of the duration. So this is the duration times the weights. So you will get the Macaulay duration of 4.62. And this Macaulay duration also can be derived using this formula. So this formula, basically, if you see here, this is the present value of each single cash flow divide by the price of the multiple cash flow. So this will be the weights times the duration. So you will do this for all of the single cash flows in the multiple cash flow duration, multiple cash flow asset. So if we use leverage on this formula, we will end up with this solution. So if you can see, since the bond consists mostly of the coupons that are level annuity, computing Macaulay duration with this formula is going to be easier, because we can leverage on the increasing annuity formula to calculate the T times the present value of the coupons in the numerator. However, don't forget to add the redemption value component in the numerator as well. We then use the normal bond price formula to compute the denominator. So by doing this, we will get the same answer. So what is the duration of a perpetuity? For a perpetuity, we still use the same formula as before. However, our T will then approach infinity. So if it's a level perpetuity, then we can leverage on the increasing perpetuity formula for the numerator, and then the normal perpetuity formula for the denominator. Okay, let's see an example. We have a 15-year, $1,000 bond with 8% annual coupon, which sells at par. What is the Macaulay duration? Okay, because it sells at par, it also redeemed at par. So we have extra clue. So we know R is equals to I, P is equals to C because it sells at par, right? And C is also equals to F because it's redeemed at par. So when we want to find the Macaulay duration, we do the formula like just now. Sum of VTAT times T over sum of VTAT, right? Which is just, it can be written as follows. The coupon we will compute T times PV by using the increasing annuity formula, and then this is the redemption value component, T times the present value of the redemption value divided by P. For this special case, it will be a lot simpler because we can simplify this formula by a lot. Now, firstly, we know that F is equals to C is equals to P, so we can remove those from the equation, and then we're left with this. We can convert this part into this equation, and then once we wrote this equation, we know that R is equals to I, so we can cut that one down, and once we cut that one down, we can also remove this part. So what we're left is just this. Sorry, it should be written like this: A angle N at I, or it will be just this. So when the bond sells at par and redeemed at par, the Macaulay duration is a very simple formula as follows: A double dot angle at I%. What if the problem involve a semi-annual coupon bond? So for a semi-annual coupon bond, you can just find the duration using the method below, before this as well. However, this formula, our unit period is semi-annual, so our our R is semi-annual, our N is also our unit period is semi-annual and not annual, right? So when we compute this, we are getting the weighted average duration in a semi-annual term. So for example, we get the duration is, let's say, 10. So this is 10 is as 10 semi-annual. So if you convert it into annual, it becomes 5, right? So that's why we are multiplying with 0.5 to convert this semi-annual Macaulay duration into the annual term. Okay.